tough act to follow with these two. Okay, great. Just a quick introduction. My name is Dylan Wood. I'm an assistant professor of architecture in the School of Architecture and Environment at the University of Oregon, and I'm a frequent collaborator now with Judith and Ian and all of the guys at TallWood Design Institute. I'm going to share today a couple of different projects throughout the day, but we'll start with one that is brand new, so we haven't actually started yet. But it's also very forward-looking, so it should be exciting to have a look. This one is called Robotic Connections, and it's about developing a material-aware robotic process for machining, inserting, and fixing prefabricated timber connections. And it's really also quite cool that now we start to involve some other departments and faculty at OSU and also at UO. But for this one, we're working with Professor Ross Hatton, who is an associate professor in the robotics groups. There are a couple of them on campus here. And so we're working like sort of half-half with his team on developing this. And we're also really fortunate to be working in close collaboration with Timber Lab, which I guess most people know here, Swinnerton's research and development team, and also KTM Research, which is a small automation engineering company outside of Portland, which is also OSU graduate founded. And this is the first time that we're all working together, but we hope that it will go well. The project starts from like just a sort of like slightly larger view of what connections are. So we know that, of course, in mass timber, especially in seismically active areas, metal or steel connectors are really, really important. And while most of the work here focuses on the timber part of things, the connectors are critical. And there's all different kinds, but historically, these have sort of emerged from on-site construction, and now they have the types of connectors that you see have gotten like much better designed over the past, I don't know, decade, specifically for mass timber and even more for prefabrication, but they come always from this sort of craftsman putting them in on site. And now they're getting better, but most of the engineering or most of the work on the connectors focuses purely on the engineering aspects, and it's getting really good. And we have a lot of great companies in the US and also in Germany and Europe that have sort of refined these. But even in the most advanced companies like Timber Lab, for example, we mill the pockets or the recesses or the alignment parts for the connectors, but then they get inserted by hand. So this is like a part of the process that is not automated and not digitized. Like it's digitally planned for sure, but the physical part of it is not digital or automated. And it also represents like a sort of gap in this chain of digital production. And in many ways, because of course we know wood has variable properties, even when we turn it into mass timber, it still requires a lot of like sanding or finishing and placing them in. So this process of placing them in is one part of it, and then fixing them is another part that I think most people, if you've ever screwed these really long screws in many times, you would understand that it's not something you want to do for like 8 hours a day. And this like clearly represents a kind of like gap in this chain that would enable things to get a bit further. At the same time, there's been a lot of development in robotics for machining, and this has become much more advanced over time. There's also been in research and development, like internationally, there's been a lot of work in like how we can do different parts of the processes, like machining or fixing with nails or lifting panels, but really like connectors, we haven't seen much of that. And the other part of this from more like the robotics side, which is really interesting for us as researchers, is that with machine learning and feedback loops where the robot is like actually has some sensor or some feedback, the machines can actually start to have more like behaviors. So if you imagine trying to push a plug or a piece of metal into the wood, there's a certain amount of like human craftsmanship and force feedback that you have in that. And what we're seeing now on a technical level in research is that is happening, like that's starting to happen. So robots can start to feel their way around rather than just moving to a specific position as they have done historically. So they're getting smarter, and we shouldn't be scared yet, but but part of what we're trying to do is like then now this is a sort of really nice opportunity where we can take some of this work that has been done by other groups and that I've also been roughly involved in, and we can start to implement this in an application that we have identified as a sort of bottleneck in this digital chain for mass timber. So that's sort of the background of it. What we're going to do, we're going to develop the system. It has to be material aware. So that means that like the robot knows where it is. It sort of can learn a bit about like that it's working for timber and not precisely machined steel. And then we're going to address these three challenges. Can we machine the parts even better? Can we insert the connector, and can we also fix it with these long screws? So this is more for outside the mass timber world, but like so you understand what these types of processes look like and these types of connectors. I mean, if you were to X-ray this, there's tons of screws, right? So it's not just what you see it's like an iceberg. It's not what you see on the surface. And then just these are very rough graphics, but this is sort of how we're going to attack this. We have machines here at Emerson and of course in the companies for machining. And then we will probably have some sort of vision system for orienting our robots and our like sort of system around it. And then we'll develop an end effector for placing and fixing. And yeah, these are the robots that we already have. So we'll use those in the process before we get new ones. And this is sort of what we imagine that this will look like. We're trying to make this also a very flexible and adaptable system. So because we have the vision system, we don't necessarily need to always have like a huge machine around the part. That's also something from advanced manufacturing that's becoming bigger now. So we can sort of like have small systems that know where they are in relation to these big parts, and then position themselves without having like a huge amount of infrastructure. We're going to do this over 2.5 years, first in OSU and UO labs, and then we'll transition it to Emerson, and then hopefully we'll also be able to then transition at least part of it into a real factory setting. Some of the tangible outcomes, I mean, we not only want to increase the sort of precision and the speed and the automation, but I think for me as an architect and also designer and engineer, what's really interesting is that would be the next step, which is that if the robots can do this, then there are probably types of connections that right now we hear as architects or engineers are not machinable or not fabricatable. I hear that all the time, right? It's like such a common thing that then we might be able to widen out what we can use. And I think that's the really, really exciting part, is that we might be able to develop new types of connections or systems that maybe a single craftsman can't do 8 hours a day, but that we would be able to enable through this. And the dissemination will be that, of course, we'll pilot this in a physical setup, and we'll also be able to apply this to the findings in this towards larger grants and further projects. And this is, of course, funded from USDA, ARS, as are most of the projects here. We have support from TallWood, and then, of course, we have the time and effort from our industry partners, Timber Labs, Winterton, and KTM. Thanks a lot.
So I'm going to invite Ian up here, and he is going to lead our Q&A section for the manufacturing and supply chain. So there are 2 microphones in either aisle. So if anyone has a question, feel free to line up and share your question there. They should be turned on and live, so I'll pass it over to Ian.
Okay, if anyone has a question, please just stick up your hand and either go to the aisle, or maybe one of us guys can help pass you a mic if you're in the middle somewhere. Okay, there's one question over there. Thanks, Nancy.
So,
Oh, I'm sorry. Well, Nancy, why don't you go, and then we'll pass the mic back to this gentleman here.
so can you hear me? Hi, it was great to hear what you're doing, Dylan. I'm really curious about what kind of sensors you're using. Is it to the robots would sense sort of the density of the wood through pushback? Or is it a visual thing where you are doing the what's metal versus what's wood? Or would it be something like the ultrasound that we saw in the last project where you could see where all the fasteners are already so you don't hit anything? I was just curious about what your thoughts are in terms of how you're going to use these really smart robots. What kind of feedback are they going to be using?
Sure. The short answer is the cheapest and the simplest. So, which is not necessarily because of cost, but in terms of like data management, like of course we always want the lowest amount of data that we need going in because it's easier to process and then we can process it faster. So the robots that we have and for what we're showing, it's not we may work also with Vahid on a different project where we use the ultrasound, but here we're not trying, we can't change the wood, right? So we're going to, it's more about like feeling. So it's probably, we will use like force torque sensors, which are multi-directional, which are like normal in robotic applications. So it's like you imagine the end of the robot has something that can tell it where the force, in which direction the force is when it pushes. And then there is a feedback loop that we can adjust the movement. So rather than a normal planning where you path planning with a robot where it's like an offline planning, you say go to this coordinate or this plane system. Here the robot is actually like asking back to the server every, I don't know, 10, 12 milliseconds where it should go next. And then in the background, there is a calculation, which is like saying, okay, if there is this much force, then go here, if not. So you're like calculating the path like more live. That's like the simple way to explain it. How you process the information in between, there's like many different ways, but we always want the simplest sensors. So cameras are really big right now because you can get a lot of information pretty quickly from cameras. But if we don't, we can't get force from cameras, only like placement. So probably just force feedback or a couple of lasers. But we have a few other projects where we'll use cameras, but you'll see those next year, hopefully. Any other questions?
Oh, yeah, there's a gentleman here. Hopefully, question for us. You?
Hi, Dylan, this is a question for you as well. Could you talk a little bit about the vision of using robots both for fabrication in a factory setting and then installation or assembly on a construction site setting?
Sure, of course. So those are very, you might know, of course, those are very separated also in construction robots. So there might be, I don't know if Joel is here he does more construction robots in the College of Engineering. No, or like sort of on-site construction type stuff. These are very different fields. When we started out this project, discussing with the timber, with the partners, we also proposed like a variety of different topics. This is the one where we thought we could have the most impact like now, because it's like a current challenge. And we're looking at other applications like on-site that would help. But as you know, with the prefabrication, we want to like the more that we can do and better we can do in the prefabrication, then the less that we have to do on the site, right? So rather than getting a super complicated robot on the site, where it's still more expensive to have robots on the site than in the factory, and then they get dirty and whatnot. We try to aim more for the on-site or the in-factory stuff like right now. But I think that this will come, for the on-site stuff will come. These are very different. They need to deal with more dynamic situations, much more dynamic than the dynamics that we talk about. I think in the factory, I think something that we're trying to see, and it's also really interesting working with people that are in automation engineering because they have totally different views of that. They think that even maybe the most advanced mass timber factories are still kind of like not up to date in terms, if you imagine like an Amazon factory, for example, like where there's no one on the floor. There shouldn't be anyone in the floor. We're maybe getting there, but maybe one thing that we're also thinking about is how we can distribute those systems. So I talked a bit more about that before, but right now we have really big machines, like right for the CNC that have to like encapsulate the parts. And this works and they're very task specific. But then of course, when you need to change them, it's a lot of money and a lot of time. And so I think in a lot of other industries, they've become much more agile with this. So they can like set up a factory, or if they have a new process, they can set up a new process really quickly because they use more generic machines that are then configured in different ways. So they're reprogrammed to work in different ways. So maybe imagine like a lot of smaller robots moving around the factory and the pieces moving around the factory. I think that's kind of like, that's the future that I think will happen, at least in the factory.
Any other questions for Dylan? If you do have a question about the second presentation, by the way, if you contact any of us at TDI, we'll get the question to the researcher and get an answer for you. All right, going. All right. Oh, Maria Paula. That's right, yes. So Maria Paula, if anyone does have a question about the second presentation, Maria Paula, who's working on that project with Fahid, can answer. Or she can try to answer, she said. All right, not hearing any. All right. Okay, I'm gonna pass back.
Thank you. Thanks for asking questions. So we're a little bit ahead of schedule since we glossed over Leck's presentation. So we're slated for a 10-minute break, which we can take now. We'll be back in this room at 10:45. The schedule says 10:58, so just adjust that in your mind. 10:45, be back in here. We'll take a short break. Thanks, guys.